Welcome to the third lecture of week two. In the prior two lectures, we put together two important aspects needed to understand consumer decision making. So, we looked at how we could represent preferences of the consumer over the given two goods, and then we also learned how to represent the budget constraint that the consumer faces. Now, we look at the actual choice and how this choice is made. The simplest principle underlying this choice is that the decision maker chooses its most preferred alternative from those available to it. Now, the available choices constitute the choice set. Given this, we just have to figure out which one would be the most preferred bundle that would be chosen. So let's work with this figure. So this is your three-dimensional figure which you saw in the lecture video on utility. So we're trying to figure out what's the optimal quantity of x1 and x2 uh, given the choice that we have. Of course, as a consumer, we would like to go as high as possible, but we cannot choose any higher indifference curve because we are constrained by how high we can go by our budget constraint. That's what you see here. This blue line here is the maximum, it's the budget constraint. It's a three-dimensional representation of the budget constraint, and it basically tells you how high you can reach on the utility surface, which you saw before in the utility video as well. Now, let's stretch it out on two dimensions again and see how does this point where the highest possible indifference curve that could be reached given the budget constraint looks like on a two-dimensional diagram. So this is how it will look on the surface, and now let's figure out how it looks like on a two-dimensional diagram. And so now you can see that indifference curves are the board-in curves. They are convex to the origin. These are basically called as the well-behaved indifference curves. And this blue line here is the budget constraint. And we can see that the blue bundle here is the most optimal bundle that this consumer could have. Notice that the brown bundle here, or the bundle denoted by the brown color, is still an affordable bundle. But if you think about the level of satisfaction that this consumer is getting from this bundle, then that level of satisfaction is certainly ranked lower than what he or she could achieve with uh, the bundle represented by the blue color. And so that is your optimal bundle. That is the indifference curve on which, or the highest indifference curve that you can reach given your budget constraint. So all the bundles on the left hand side are affordable bundles. So you could afford either of them. The point is that if you are working to maximize your satisfaction given your consumption, then you would try to reach as high as possible on the indifference curve given your budget constraint. And that's exactly this point here. So these are the preferred bundles on this. The highest you can go is this. If your income changes, income increases, and obviously you will be able to reach a higher indifference curve. So let's look at the clean diagram. So all the bundles to the right hand side of the most optimal point are basically more preferred bundles, but you cannot reach there unless there is a change in price of either commodities or change in income. We will call these bundles, or we will call the units in units of x1 and x2 in this bundle, optimal bundle, as x1 star and x2 star. Notice that the optimal bundle uh, is the most preferred bundle, but it is also the most affordable bundle that the consumer could have. The most affordable bundle is called the consumer's ordinary demand at the given prices and budget. Ordinary demands will be denoted by x1 star, and we will write all the arguments from the budget constraint in the bracket. It signifies that x1 star is x1 star because of p1, p2, and m. So if these change, then x1 star is going to change. Similarly, x2 star also has the same arguments in the bracket. If you're mathematically inclined, it basically means that x1 star is a function of price of x1, price of x2, and the total income that is available. Similarly, x2 star is a function of price of x1, price of x2, and m, which is the total income available. When both x1 star and x2 star are positive, which means that the consumer buys a bundle in which both of these commodities are consumed in a positive amount, then we say that the demanded bundle is interior. For such a bundle, if it costs M dollars, then the budget is exhausted. So you can see that x1, x2 is interior. It basically means that there are positive amounts of both x1 star of both x1 and x2. The second property is that it exhausts the budget. It's exactly on the budget constraint, and so it exhausts the budget. What else can we say in terms of characterizing the optimal choice? Notice that the blue point here, or the bundle represented by the blue point here, is common to both the budget constraint and the indifference curve. Also, the budget constraint touches the indifference curve exactly at this point and does not touch the indifference curve at all at any other points. So we call the budget constraint as being tangent to the indifference curve. And the blue point is such that the slope of the indifference curve at the optimal choice is equal to the slope of the budget constraint. Now remind yourself of what is the slope of the budget constraint before you move on to the next slide. So how would we define rational constraint choice? It satisfies two conditions. It lies on the budget constraint, which means it exhausts the budget constraint. It exhausts all your income. You end up spending all your income if you buy the optimal bundle. The second point is that the slope of the budget constraint, which is negative P1 by P2, and the slope of the indifference curve containing the bundle are equal at the point which is used to represent the optimal bundle. The question is, how can we use this information to locate x1, x2 for a given p1, p2, and m? Let's look at one example. Now this utility function here is called as the Cobb-Douglas utility function. So it's a multiplicative utility function. I'm saying that utility of x1 and x2 is a product of x1 and x2. But it's not only that. x1 is raised to a and x2 is raised to b. So it's a power function. It's a product of two power functions. Okay. Now what is a and b? Generally, a and b are the expenditure shares in the total expenditure of money spent on x1 and money spent on x2. The property of Cobb-Douglas preferences is such that if we know that overall, over a period of time, the share of expenditure on x1 and share of expenditure on x2 has remained constant, then we can represent the preferences of the consumer on x1 and x2 by this utility function, which is called as the Cobb-Douglas utility function. So most of for example, think about categories of commodities on which you spend. So let's say you spend your monthly income on food and groceries and transportation. Most likely, unless you take a vacation and drive somewhere, your expenditure on food and expenditure on transportation is going to be more or less a similar proportion over a period of time. You might spend 70% of your income on groceries and 20% of that on transportation, and this would remain constant. Then, if I ask you how would we represent your preferences over food and transportation, this is exactly given by the Cobb Douglas preferences. What are the advantages of doing that? If I graph the Cobb Douglas preferences, they look exactly as the convex indifference curves, and so it's a good example to work with. Let's figure out if this is the utility function, then what is the slope of the indifference curve implied by this utility function? It turns out that the slope of the indifference curve is given by this ratio here, which you would know as change in x2 divided by change in x1. This is derivative. We are looking at a very small change, and therefore instead of using a triangle delta to represent change, we are using d, signifying a very small change. So it's like slope of any curve. It's basically rise over run. Indifference curve, on the x-axis, the rise is change in x2. On the y-axis, run is basically change in x1, and this is the ratio of the rise over run. It turns out dx2 is basically the marginal utility of x1, which means if I increase x1 by one minute unit, then how much of that adds to the utility? The same I do for x2 as well. Now go back a little bit and see what the marginal utility for both of these goods look like. Now I don't expect you to actually know the derivatives. I will give you the marginal utilities that are computed. All you have to do is to figure out the slope of the indifference curve. You have to divide marginal utility derived from the first commodity by marginal utility derived from the second commodity. And when you do that, this is what you get. So the indifference curve implied by a Cobb-Douglas preference has a slope or marginal rate of substitution given by minus ax2 by bx1. Again, remember, A and B are the shares, expenditure shares on x1 and on x2. Now we know that at the optimal bundle, MRS is equal to minus P1 by P2. So all we need to do is figure this out, we need to equate the slope of the indifference curve with the slope of the budget constraint. Then we basically solve for one of the variables. Now you can see that all this equation A gives you is how does x2 vary with x1. But of course, this doesn't give us a solution. Now there are two variables, and if you want to solve for two variables, you have to have two equations and not one equation. So where do we get the second equation from? Remember, the second property of the optimal bundle is that it exhausts all the budget constraint. You end up spending all your income on this optimal bundle. So we are going to use that. So your second equation to figure out the optimal bundle is going to be the budget constraint. Now once I know that, it's pretty easy. So I know that x2 is equal to this expression here, which is expressed in terms of x1. I can go here and substitute that. Right? Once I substitute it, then you can, once I substitute for x2, then you will realize that the whole equation only uses x1. I suggest that when you're actually looking at it, you actually write this down on a piece of paper and convince yourself that the whole equation becomes only in one variable, that is x1. And so then it would be easy to solve for just x1. Take x1 common, and this whole thing is in the bracket, which you can use. So it turns out, after simple algebra, x1 is equal to, x1 star is equal to a, which is the expenditure share on x1, divided by the total of the expenditure shares, which is usually going to be 1, divided by p1. So all that you're basically saying is that your preferences, if they can be represented by Cobb-Douglas, then the optimal amount of x1 that you will buy depends upon the total income that you have, how much of um, how much of x1 that you can buy if you spend all of your income on p1, and then multiply that by expenditure share, and you get the optimal amount of x1 star. Once you substitute for x2 star, that is what you get. The interpretation again is similar. B is the expenditure share. M divided by P2 is the total amount of X2 that you can buy if you spend all your income on X2. But of course, because we are using a convex indifference curve, there are no corner solutions here. So here, X1 and X2 are always going to be positive. So in order to figure out how much X2 is going to be, you have to multiply by the expenditure share. So we have discovered that if our preferences can be represented by Cobb-Douglas function, okay, and the condition that when it can be represented that way is that the expenditure share of x1 and x2, that is basically two commodities, when it roughly remains constant over a period of time, then you can represent your preferences over these two commodities by the Cobb-Douglas utility function. Then the optimal bundle is given by this expression. How does it look on the graph? So, just to recap what is or how we found the rational constraint choice, when x1 star and x2 star are both positive, which means they are interior, and x1 and x2 star exhaust the budget, which means you end up spending all the money income on that, and if the indifference curves have no kings, which means they're not right angle triangles or something like that, which means we are assuming here they are well behaved, they are convex to the origin indifference curves, then the ordinary demands, which is nothing but the optimal bundle, are solved by using two equations. One, the budget constraint, which when evaluated at the optimal bundle implies that you are basically exhausting all your income. And two, remember, the optimal bundle is given by the point of tangency between indifference curve and the budget constraint, which means at that point, at the optimal point, the slopes are equal. So you take the slope of the budget constraint, which is minus P1 by P2, and equate that to the slope of the indifference curve. Once you do that, you get the optimal bundle. All right, now I suggest that you take the utility quiz, the choice quiz after this lecture, just to make sure that you have got all the points.